Okay, so let's continue from last time. Uh, okay, okay, I think I just finished studying the theorem last time. So, okay, so maybe let's start with some like script here. So, like, um, okay, okay, so maybe let's recall something. So here, we have this X as X tutor as the universal covering space of X, and then we have the covering map gamma, and then we have this space as X, where this X is the universal covering of a this X is a connected locally simply connected, locally compact Hausdorff space. Okay, so it's connected. Locally simply connected. So I'll use letter like this letter for simply connected, and then locally compact Hausdorff space. Okay, so and then this gamma is the depth transformation, and then so this gamma is okay. So yeah, so basically the idea is that we have this commuted diagram, right? So this is like the it's like the gamma of gamma, and then here it's like gamma take away x tilde. Yeah, so yeah, so this is like the quotient space x tilde quotient by the equivalent equation by this gamma, where at any 2 points they are equivalent to gamma is that this so this there is element, let's say small gamma from the big gamma, so that gamma of one element is equal to the other element. Yeah, so that's that's the definition of this one. Okay. So then what we have, so okay, so this is a homomorphism. Okay, so moreover, okay. Okay, so okay, I think the conclusion is that yeah, so this gamma, which we define as the depth transformation of this big gamma x, properly discontinuously on okay, and freely on this x student. Okay, so then uh, okay, so one, and then number two, so the quotient map, so this gamma of gamma from this x student to this gamma take away x student is a common map. And number three, yeah, so this is number three. Okay, sorry. So number two is that this is a covering map, and then number three is that this is so this diagram is commutative. And the mapping so it's a homomorphism. Okay. Alright, so here is the square words here. So in outer words. So again, so this is not a proof, this is like some explanation. So this gamma of this small gamma from x student to this gamma take away x student is a covering that we may identify with the original covering. Covering gamma from x tilde to x. Okay. 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 So then it follows that if gamma hat from x tilde to x hat is a user covering space a connected, locally compact Hausdorff space F hat. Okay. So of a connected locally similarly connected and locally compact Hausdorff space. Okay. I've said. Okay. And then the depth transformation of this gamma hat is equal to the depth transformation of this gamma. Oh, okay. Oh, okay, I see. Okay. Then this we have this x hat, which is as homomorphic to this x hat. Gamma is equal to x hat, which is homomorphic to x, and we can identify the coverings. Identify the coverings. Is gamma hat from x tilde to this x hat, and it's gamma from x tilde to x. Okay. All right. So yeah, let's come back to it after we do the proof. Okay. So okay. So here let's say the proof. Okay, so the proof. Okay, here it says part E of theorem 10.4.2. Okay, so theorem 10.4.2. Okay, so yeah, part E says that each element phi of this dash transformation of this gamma take away the identity has no fixed y. Okay, we show that. In fact, if U is an evenly covered domain in X, u naught is a component of this u tilde, which we define as the gamma inverse of u. Then the set u1, which we define as the phi of u naught, is a where this phi is one of the that transformations. Yeah, so it's one of the transformation that is not identity. Okay, it's not identity. And then it's the u1 is being defined as phi u naught, which is a component of u tilde that is distinct, where destroyed from u naught. Yeah. So basically, this lemma says yeah. So basically, if you pick evenly covered set, then the image of this you take one of the component of the pre-image of this set U, right? So pre-image under gamma. So because the pre-image under gamma is this union of like open sets, and then you take one component of it, and then you apply the transformation. Then that image is distinct from the original one. Yeah. Okay. So let's see. And of course, this U must be a evenly covered domain. Like open connected. Yeah, it has to be connected. Okay. Alright, so okay, so this is part E. Okay. So so part E of theorem 10.4.2. Yes, the one that we just discussed, and lemma. So so here is the lemma. So yeah, so this lemma. So this lemma here is the lemma that we stated last time. Yeah. So we just prove that. So where is like if you have a function, if you have a what's it called? Yeah, so it's lemma of like about like if you have like you have some group of the group of self-homomorphism of a locally common holomorphic X, then this subgroup we call it gamma. So yeah, we call it subgroup gamma. Then this gamma acts probably discontinuity on X. You can only be for each pair of points x1 in X. There's a neighborhood U of X and V of Y such that this a small gamma U in V is empty for all but finally many element small gamma of big gamma. Yeah. So this is the lemma that we proved last time. Or like last lemma we proved. Okay. So and lemma. Four. So this is lemma we showed like variable. Together imply that so this gamma acts properly discontinuously and freely. Properly discontinuously and freely. Okay, so let's see why this is true. So Okay, so here I conclude that this gamma makes the property discontinuous and freely. Oh, okay. Okay, let me see. Okay, so let me think. Um, Part E of theorem 10.4.2 at the lemma 10.4.2 together imply that gamma x probably discontinuously and freely. What do you mean by part? Okay. So this gamma is what? So this gamma is yeah. So this gamma is the Dirac transmission group, right? So I want to show that this acts properly freely. So this gamma is the Dirac transformation group. So it acts properly discontinuously means on X if any compact set Kx, gamma k in the case empty for finitely many. It's not empty for finitely many element gamma or small gamma. Okay. So okay, I want to show that. Okay. Okay. So this 10.4.4 says that okay, so let gamma be a subgroup of the group of self-homomorphism of a locally compact Hausdorff X. Okay. So then this gamma x probably this discontinuity on X even only be for each pair of points x, y, x. There is neighborhood u of y, u of n. Yeah. So yeah, so basically this is like an equivalent statement of the probably the discontinuity on this X, where this X is a locally compact Hausdorff space. So even only for each pair of points x, y, x. So let me think. Okay. So let's see. I want to show that basically, yeah. So basically, this one is equivalent of saying that for each point x, y. Let me see. So this is the equivalent of saying that. Okay. Yeah, I know the definition of freely is all stated in here. Okay. Okay, never mind. Let me think. So basically, we want to show that for each pair of points x, y, and x, right? So okay. So here we want to say it's x tilde. Okay. So namely, so what we want to show is that so for each pair of points, so that x, y be in this x tilde, then so we want to find a neighborhood, right? So turns that okay, so it's small gamma. Okay, small gamma. Small gamma of U intersect V is non-empty. So finally, many small gamma and big gamma. Okay. Okay, so so let's see why is it true. So neighborhood U of X, V of Y. Oh, I see. Okay. Okay. So by the way, this is not yeah. So this is just about like a property discontinuity. Discontinuity. Okay. Yeah, I will use the letter DIC like a little bit to explain. Okay. Okay. So let's see why there is never be over. Here maybe because B is not defined in many gamma. Okay. So I could probably read. Okay, so theorem 10.4.2 give me what? So, U of X, V of Y, such that U is an evenly covered domain in X. Okay, so let's try first to test. Okay, suppose this is X. Okay, so suppose this is like X here. Suppose we have the Y here. Maybe that's suited to X tutor, Y tutor. Okay. Because I want to use the covering projection here. Let's project it down to X. Let's project it down to Y. Then what happened? So, U of X is a Y tutor. Hold on. So here, because this X is connected, locally simply connected, right? So because yes, I think I can pick a locally compact set, right? Locally connected set. Yeah, let me check. Okay, yeah, so I can pick a simply connected, like like domain here. Let's call this U. Maybe let's call it sorry. Let's call this U here. Let's call this V here, and then so they may be destroyed or they may not be destroyed. Okay. Okay. So here I get a lift. Okay. 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 So let's assume that these two are like separated. Okay. Can I make them separated or it's not assumed? Wait. Can you take two sets separated? Let me see. Can they only separate like twice, right? Like household space. Wait. Yeah, I think it's household space, right? You can make a separation, right? Yeah. Yeah, so you can separate them. So yeah, yeah, okay. Separate them and then you take the pre-image becomes here, and then so can the no, the pre-image must be destroyed, right? Otherwise, if they intersect, then it will intersect. If they intersect on the top, then what happens? If they intersect on the top, then if they intersect at the top, then if you do a okay. Yeah, it will be intersecting. Okay, yeah. Okay, so they must be destroyed. So okay, so in this case, right? So in this case, so if they are destroyed, then you apply the depth transformation, you get nothing. Why you got nothing? Because if you apply any element of the depth transformation into this U2, it would only lie in this, because you have this gamma of this U2 must be lies in the gamma inverse of gamma inverse of U, right? And then similarly you have this this is like and then similarly I don't think you need the other thing, right? So and since so since you have this so since U intersect B is empty, so therefore I want to say is that I want to say this gamma inverse of U gamma inverse of U, and then it's intersect with gamma big gamma inverse of B must be empty set, right? If not, then you pick X as that's in both gamma inverse of U and then gamma inverse of B. So therefore this gamma of this element must lie in the intersection of this U and B, So therefore that holds the proof. Okay. So it must be empty. So okay. So what happened? So Yeah, so they are empty. So since this lies in gamma inverse of u, right? Then it can lies in, yeah, it can lies in gamma inverse of v. So therefore, and this v tilde it lies in gamma inverse of v. Therefore, this 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 holds. Okay. Okay. So yeah, right. Wait. It's so easy. I don't think so, right? Because wait, is that something? Um, uh, wait. Oh, okay, okay, I think so, yeah. Because, okay, I think the idea is that, I think if you can do that, then it will be totally discontinuous, like totally empty, okay. Yeah, it will be totally empty. So, but I don't think you are allowed because, yeah, so remember, yeah, I think I did something bad here because even though you have separation, but you don't have the separation as the evenly covered, right? So the evenly covered doesn't come together like, yeah, because you because yeah, this you already have the like the destroy union property. You want to have this u and v, they are evenly covered, evenly covered, right? So I don't think you can pick the evenly covered using like the Hausdorff condition, right? So yeah, so there is no guarantee that this U and V exists, okay, by the even and as evenly covered set. So uh, yeah, so we have to we can just say that they must be destroyed, right? So maybe they, yeah, yeah. So maybe there are some exceptions. So uh, so what happens if they intersect with each other? What happens? So um, so let me see the. Okay, so I think the idea is that okay, I want to use a